Today we're diving into the world of traditional databases, the backbone of digital information storage for decades. From banks to hospitals, these systems quietly power our daily lives, ensuring that data is organized, accessible, and reliable. But what exactly makes a database traditional? In this video, we'll explore their core features, focusing on security and transparency, and see why they remain so vital in our technology-driven world. Let's start by understanding what a traditional database is and why it's so important in modern society. Traditional database is a structured collection of data, typically managed by a database management system, or DBMS. These databases use tables, rows, and columns to organize information, making it easy to store, retrieve, and update data efficiently. Think of them as digital filing cabinets where every piece of information has its place. Popular examples include MySQL, Oracle, and Microsoft SQL Server. These systems have been trusted for years to handle everything from financial records to customer information, thanks to their reliability and robust design. Traditional databases are built on several key components. At the heart is the DBMS, which acts as the interface between users and the data. The DBMS handles tasks like data storage, retrieval, and security. Databases also include schemas, which define how data is organized, and query languages such as SQL that allow users to interact with the data. These components work together to ensure data is not only stored but also easily accessible and well protected. Security is a top concern for any database. Traditional databases employ a range of security measures to protect sensitive information. These include user authentication, access controls, and encryption. Only authorized users can access or modify data, and every action is logged for accountability. Encryption ensures that even if data is intercepted, it remains unreadable to outsiders. These features make traditional databases a trusted choice for organizations handling confidential data. User authentication is the process of verifying the identity of anyone trying to access the database. This usually involves usernames and passwords, but can also include multi-factor authentication for added security. By confirming identities, databases prevent unauthorized access and keep sensitive data safe. This layer of protection is essential, especially in industries like finance and healthcare, where data breaches can have serious consequences. Access controls determine what each user can see or do within the database. Administrators can set permissions, allowing some users to view data, others to edit, and some to manage the entire system. This granular control helps prevent accidental or malicious changes, ensuring that only the right people have the right level of access. It's a crucial part of maintaining both security and data integrity. Encryption is a powerful tool used by traditional databases to protect data at rest and in transit. When data is encrypted, it's transformed into a code that can only be read with the correct key. This means that even if someone intercepts the data, they can't make sense of it without authorization. Encryption is especially important for sensitive information like credit card numbers or personal details. Traditional databases keep detailed logs of every action taken within the system. These audit trails record who accessed what data when and what changes were made. This transparency is vital for detecting suspicious activity, investigating incidents, and ensuring compliance with regulations. Audit trails also help organizations demonstrate accountability and maintain trust with users and stakeholders. Transparency means that actions within the database are visible and traceable. This is achieved through clear documentation, audit logs, and well-defined processes. Transparency helps organizations spot errors, prevent fraud, and build trust with users. It's especially important in regulated industries where proving that data is handled properly is a legal requirement. Data integrity is all about ensuring that information in the database remains accurate and consistent over time. Traditional databases use rules, constraints, and validation checks to prevent errors and unauthorized changes. This means that the data you retrieve is reliable and reflects the real-world situation it represents. Data integrity is crucial for making sound business decisions and maintaining operational efficiency. No system is immune to failure, which is why traditional databases include robust backup and recovery features. Regular backups ensure that data can be restored in case of hardware failure, cyber attacks, or human error. Recovery processes are tested and documented, so organizations can quickly bounce back from disruptions and minimize downtime. This resilience is a key reason why traditional databases are trusted by mission-critical industry. Role-based access control, or RBAC, is a common security feature in traditional databases. It assigns permissions based on a user's role within the organization, such as administrator, manager, or regular user. This approach simplifies management and reduces the risk of accidental data exposure. By grouping users and assigning roles, organizations can efficiently control who can access sensitive information. Beyond digital protections, traditional databases also rely on physical security. Servers are often housed in secure data centers with restricted access, surveillance cameras, and environmental controls. These measures protect against theft, vandalism, and natural disasters. Physical security is an often overlooked but essential part of a comprehensive database protection strategy. Database firewalls act as a barrier between the database and potential threats from the internet or internal networks. They monitor traffic, block suspicious activity, and enforce security policies. Firewalls are a critical defense against cyberattacks, helping to prevent unauthorized access and data breaches. Keeping database software up to date is vital for security. Patch management involves regularly applying updates and security patches to fix vulnerabilities. This proactive approach helps protect databases from new threats and ensures that security measures remain effective over time. Any organizations must comply with regulations like GDPR, HIPAA, or PCI DSS, which set strict standards for data security and transparency. Traditional databases are designed to help organizations meet these requirements through features like audit logs, access controls, and encryption. Compliance not only avoids legal penalties but also builds trust with customers and partners. Data masking is a technique used to hide sensitive information within the database. For example, credit card numbers might be partially obscured, showing only the last four digits. This allows data to be used for testing or analysis without exposing private details, adding an extra layer of security and privacy. Monitoring tools track database performance, usage, and security events in real time. They alert administrators to unusual activity such as unauthorized access attempts or performance issues. By catching problems early, organizations can respond quickly and keep their databases secure and efficient. Disaster recovery planning ensures that databases can be restored quickly after unexpected events, such as cyberattacks, hardware failures, or natural disasters. Plans include regular backups, offsite storage, and detailed recovery procedures. This preparation minimizes data loss and helps organizations maintain business continuity. Data redundancy involves storing copies of data in multiple locations. This protects against data loss if one system fails. Traditional databases often use techniques like replication and clustering to ensure that information is always available, even during outages or maintenance. There are different types of encryption used in traditional databases. At-rest encryption protects stored data, while in-transit encryption secures data as it moves between servers and users. Both types are essential for comprehensive security, ensuring that data remains protected throughout its lifecycle. Traditional databases support a variety of user roles, each with specific permissions. Common roles include administrators, developers, analysts, and end users. By assigning roles, organizations can control access and ensure that users only see or modify the data relevant to their job. Transparency in database operations builds trust with users and stakeholders. When actions are logged and processes are clear, it's easier to detect and correct mistakes, prevent fraud, and comply with regulations. Transparent systems also foster a culture of accountability within organizations. Despite their strengths, traditional databases face challenges. These include scalability limits, complex management, and the need for constant updates to address new security threats. As data volumes grow and cyberattacks become more sophisticated, organizations must continually adapt their database strategies to stay secure and efficient. Regular maintenance is essential for keeping traditional databases secure and running smoothly. This includes updating software, optimizing performance, and reviewing security settings. Proactive maintenance helps prevent problems before they occur and ensures that the database continues to meet organizational needs. Data consistency ensures that all users see the same information, no matter where or when they access the database. Traditional databases use transactions and locking mechanisms to maintain consistency, even when multiple users are making changes at the same time. This reliability is crucial for business operations and decision-making. Scalability refers to a database's ability to handle increasing amounts of data and users. Traditional databases can scale vertically by adding more powerful hardware, but this approach has limits. Organizations must plan carefully to ensure their databases can grow alongside their business needs. Protecting user privacy is a key responsibility for any organization using traditional databases. This involves not only securing data but also limiting access to only those who need it. Privacy policies, data masking, and strict access controls all contribute to safeguarding personal information. Performance optimization ensures that databases respond quickly to user requests. Techniques include indexing, query optimization, and hardware upgrades. Fast, efficient databases improve user experience and support business operations, making performance tuning a top priority for administrators. Failover systems automatically switch to a backup database if the primary one fails. This ensures continuous availability and minimizes downtime. Traditional databases often include failover features as part of their disaster recovery strategies, providing peace of mind for organizations that rely on constant access to data. Transaction management ensures that all database operations are completed successfully or not at all. This prevents partial updates that could lead to data inconsistencies. Traditional databases use the ACID principles: atomicity, consistency, isolation, and durability to guarantee reliable transactions. Indexing is a technique used to speed up data retrieval in traditional databases. By creating indexes on frequently searched fields, databases can quickly locate information without scanning every record. This improves performance, especially for large datasets. SQL, or structured query language, is the standard language for interacting with traditional databases. It allows users to create, read, update, and delete data using simple commands. Mastery of SQL is essential for database administrators and developers alike. A schema defines the structure of a database, including tables, fields, and relationships. Schemas provide a blueprint for how data is organized and ensure consistency across the system. Well-designed schemas make it easier to manage and secure data. Normalization is the process of organizing data to reduce redundancy and improve efficiency. By breaking data into related tables and eliminating duplicate information, traditional databases maintain data integrity and make updates easier to manage. Constraints are rules that enforce data integrity in traditional databases. Examples include unique constraints which prevent duplicate entries and foreign key constraints which maintain relationships between tables. Constraints help ensure that the data remains accurate and reliable. Views are virtual tables created by querying data from one or more tables. They simplify complex queries and can be used to restrict access to sensitive information. Views are a powerful tool for improving security and making data easier to work with. Stored procedures are pre-written SQL code that can be executed as needed. They automate common tasks, enforce business rules, and improve security by limiting direct access to data. Stored procedures help maintain consistency and efficiency in database operations. Triggers are automatic actions that occur in response to specific events, such as inserting or updating data. They help enforce rules, maintain data integrity, and automate routine processes. Triggers are an important feature for managing complex database systems. Replication involves copying data from one database to another, often in real time. This improves availability, supports disaster recovery, and allows for load balancing. Replication is a key strategy for organizations that require high reliability and uptime. Clustering connects multiple database servers to work together as a single system. This increases performance, reliability, and scalability. If one server fails, others can take over, ensuring continuous access to data and minimizing downtime. Security policies define the rules and procedures for protecting database systems. They cover topics like user access, data encryption, and incident response. Well-defined policies help organizations maintain consistent security practices and respond effectively to threats. Regular security audits assess the effectiveness of database protections. Auditors review access logs, configuration settings, and compliance with policies. These audits help identify weaknesses and ensure that security measures are up to date. As technology evolves, traditional databases continue to adapt. Innovations in security, transparency, and performance keep them relevant in a rapidly changing world. While new database models are emerging, the core principles of security and transparency remain as important as ever. Summary: traditional databases offer a powerful combination of security and transparency. Their robust features protect sensitive information, ensure data integrity, and build trust with users. As organizations face new challenges and opportunities, these foundational principles will continue to guide the evolution of database technology. Thanks for joining us on this journey through the world of traditional databases.